If you notice, when we've did addition reactions in the previous unit, we always did them on alkenes. What are some examples of those alkenes? Well, we love to use propene because it was small and easy to draw. We might have done some on cyclohexene or related compounds. One thing that we never looked at, we never looked at a benzene ring. And benzene ring is where we have this six-membered ring and we have three alternating pi bonds with sigma bonds between them. So this is a benzene ring. Now, as it turns out, benzene does not undergo typical addition reactions. So it's inert to most additions, which is to say it is not reactive. And when things are not reactive, we oftentimes say, oh, it's stable. Well, the stability of a benzene ring is captured by this term called aromaticity. And historically, people found that they could take molecules that were alkenes, and these alkenes would undergo addition reactions. But when the alkenes were in rings of a certain type, all of a sudden the alkenes did not react at all. These alkenes had a special stability. And so they came to call these compounds aromatic compounds. And this is aromaticity is a property of molecules that seems to impart, I'm going to call it magical, but that's a little corny, okay? It's not magic, it's science. But it's this surprising stability in alkenes. So how do we recognize this? Well, this scientists figured out how to identify compounds. And you can call these Huckel's rules, or if you're a real Deutschmeister, you might say Huckel's rules, because that U with the umlaut, you kind of has a different sound. But anyway, Huckel's rules, whichever you want to go with. Huckel found that there are 4 rules. 1, you had to have a ring. 2, all atoms in the ring need a p orbital. Okay, so let's think about this a little bit. This isn't part of the rule, but this logically comes out of these rules. So all these atoms are in a ring, and they need a p orbital. Which hybridizations give us p orbitals? sp3 hybridization does not have any leftover p orbitals. If an atom's going to be hybridized with a leftover p orbital, it's going to have to be either sp2 or sp hybridized. That means every atom in the ring is going to have to be either sp2 or sp hybridized. Well, sp hybridized atoms are linear. And when things are straight, they don't lend themselves to being bent around as part of a ring. So for practical purposes, sp hybridization is on the table. So essentially, when we say all the atoms in the ring need a p orbital, we're saying all the atoms in the ring need to be sp2 hybridized. So that's an important thing. And to talk about aromaticity, we need to be up on our hybridization and being able to identify what the hybridization of atoms are. Okay, another thing, the ring needs to be flat. It's typically not a big deal. If all the atoms are sp2 hybridized, these are going to be planar structures. And if you're building your ring out of planar atoms, it's a good chance your ring is going to be flat. So flat is normally not a problem. The last rule is the number of electrons, and these are the electrons in the p orbitals, must solve out for this formula 4m plus 2. So when we put in a number of electrons, whether it's 10 or 24 or 3, we need to be able to solve for n so that n is an integer. And it could have a value of 0, 1, or 2. Now, we won't get too exotic in here, but in effect, if n equals 0, 4 times 0 is 0, plus 2, 2 electrons. 2 electrons is a valid solution. If n equals 1, 4 times 1 is 4, plus 2 is 6. 6 electrons is a solution. And another one you encounter sometimes is 10 electrons. You can keep going, but these are the common ones. So we need a ring. All the atoms in the ring need a p orbital. Check, check. We need it to be flat, and the number of electrons in the p orbitals must be 2 or 6 or 10 electrons. Let's look quickly at benzene. Benzene has 6 sp2 hybridized atoms. It's definitely a ring. Is it flat? Well, if everything's sp2, it's probably going to be flat. And the number of electrons in the p orbitals equals 3 times 2. There are 2 electrons in each of these pi bonds in benzene. So that's 6 electrons. So benzene satisfies Huckel's rules. And we'll see some more examples about this. But this is how we identify whether a molecule, this is what aromaticity is, it's a stability, and this is how we identify it by using Huckel's rules.